Alright everyone, and welcome back to the exciting conclusion of our practice problem solution video. Let's just jump right in. So, NASA puts a satellite into space that consists of two small 32 kilogram balls connected by a 12-meter long light cable, as shown in the figure. The entire system is initially rotating at 4 RPMs, about an axis perpendicular to the cable at the center of mass. Motors in each mass reel out more cables so that the masses double their separation to 24 meters. What is the final rotational speed in RPMs of the balls? And if the initial rotational kinetic energy of the system was K, what is the final rotational kinetic energy in terms of K? So starting with A. So this is obviously going to be a momentum problem because there's no torque or anything done. And energy for something like this, there's actually work being done because the string out here is technically doing negative work on the system to lower the kinetic energy, but there is no torque. There's nothing pushing it to the side, so our angular momentum is going to be the same before and after. So initially we have these two balls, we'll call ball 1 and ball 2. And we've got I1 initial times omega initial. Omega 1 and omega 2 are going to have the same angular velocity, so we don't have to define this as its own. Plus I2 initial, omega initial is going to be equal to I1 final, omega final, plus I2 final, omega final. And if we want to simplify, which I would, we'll do I1 initial plus I2 initial times omega initial is equal to I1 final plus I2 final, omega final. Now, looking at the moment of inertia for the two balls, these are both rotating around this sort of center point here, which means that for our moment of inertia, which is going to be the moment of inertia for an object, a single object spinning around a point, we've got I is equal to mr squared for each one. What this means is that because there's two of them, they are both the same thing. They're both the same object, they both have the same mass and the same radius away from the center of rotation, so these are effectively the same thing. So I1 plus I2 simply becomes m2 mr squared. So if you want to consider each one of these things their own system or the whole thing as a system, Alright, so we can call I1 plus I2 2 mr squared, and then this r is going to change for each one. So this is going to be 2 mr initial squared times omega initial, and that's going to be equal to 2 mr final squared times omega final. If you're clever, you realize that these two m's are going to cancel out on both sides since the mass doesn't change, and we can find that our omega final is simply going to be a product or a ratio of the two radii. So we've got our omega final is equal to r initial squared over r final squared times omega initial. This is why you solve things algebraically, because things can get very simple if you just whittle it down like this. Now, here's the thing. So in the past, I've converted this to RPMs, right? But you actually don't have to do that for this one because it's asking for the solution in RPM. So whatever angular velocity, which is still what this is, rotations per minute and radians per second are the same unit of rotational measurement per time period, right? Which is what rotational velocity is, what angular velocity is. So we can leave this as RPMs because we'll get the answer in RPMs. So our initial radius is going to be half of this total length, which is going to be 6. So you've got 6 squared over our final radius, which is going to be 12 because it goes up to 24 squared, times our mass, which is 32, or times our, sorry, not our mass, times our angular velocity, which is 4. There we go. 4 RPMs. This is each going to be in meters. These meters are going to cancel out, so when we multiply everything together, we're going to have it in RPMs. And this, as it turns out, is just 1 RPM, if you were to plug that all in. Right, so the second part of the question is asking, if the initial rotational kinetic energy of the system was K, what is the final rotational kinetic energy in terms of K? So what our goal here is to write our final kinetic energy in terms of the initial kinetic energy. So let's first find out what the initial kinetic energy looks like. K is equal to 1/2, our rotational kinetic energy, right, is equal to 1/2 I omega squared, initial omega squared, right, which means that this is equal to 1/2, our I is 2, right, because we're taking this whole system, M R squared times omega initial squared. Alright, and simplifying, we can take out this 1/2. So this is just mr squared omega initial squared. Alright, that is our initial kinetic energy, is equal to this. Now let's take a look at what our final kinetic energy looks like in terms of the initial kinetic energy. So this is again 1/2 I final omega final squared. So we can write an expression for the final I, which is just going to be 1/2 times I, which is going to be 2m still, but now r is double the initial r, right? If this was our initial r, the radius doubles, so it went from 12 meters before to 24, which means it went from 6 here to 12. So I'm going to call this 2r, which is what this is, the initial one, r initial squared times our final angular velocity. And if you look, we got 1 RPM for our final angular velocity over here, and we had an initial of 4. So we can actually rewrite our final angular velocity as 1/4 of the initial angular velocity. And this again is squared, right? So simplifying, we get K final is equal to m4r squared times omega initial over 16. Simplifying here, we've got 1/4 r initial, this is r initial squared omega initial squared. And if you look, this right here is K initial rather. So this is actually 1/4 K, which is our solution, is 1/4 K initial. Alright, moving on. A ballerina spins initially at 1.5 revolutions per second when her arms are extended. She then draws in her arms to her body, and her moment of inertia becomes 0.88 kilograms meters squared, and her angular speed increases to 4 revolutions per second. What was her initial moment of inertia? So this is actually a fairly simple problem. This is again a job for conservation of angular momentum. And there's only one object here, so we can just call this I initial omega initial is equal to I final omega final. And we're looking for I initial here, so I initial is equal to I final omega final over omega initial, which, and again, we don't have to convert these because these units are going to end up canceling out. We've got I final of 0.88 kilograms times meters squared. This point is in here. Oops. We've got a final of 4 rev per second, and we have an initial of 1.5 rev per second. So you see that these revolutions per second cancel out, so there was no need to convert those to radians per second or whatever. And going through the math, we see that it is 2.3 kilograms meters squared. This was, as much as I hate to say it, a plug and chug problem. So moving right along. A uniform ball with diameter 10 centimeters, that's going to have to change because everything else here is in meters, rolls without slipping on a horizontal tabletop. The moment of inertia of the ball about the axis through its center is 2.2 times 10 to the negative 3. So for those of you playing at home, that's 0.0022 kilograms meters squared, and the translational speed of its center is 0.4 meters per second. Translational means that this is equal to the velocity. So what we've got here is a ball rolling across a tabletop. There's a straight line for you. And its velocity is 0.45 meters per second. And it has an I of, this is I, this moment of inertia for the ball, of this, and it's got a diameter of 10 centimeters, which means it has a radius of 5 centimeters. So what is the angular speed of the ball about its center of mass? All right, so this is effectively looking for just omega is equal to v over r, right? We know v, we know r. This is as simple as plugging in our v, which is 0.45 meters per second, and the radius, which is 0.05 meters, right? Which will give us an angular velocity of 9 radians per second. Alright, that's A. B, what is the rotational kinetic energy of the ball? So now that we've got that, it's just as simple as plugging in the values. Kinetic rotational is equal to 1/2 I omega squared, which is equal to 1/2 I, which we know is 0.0022 kilograms meters squared, times omega squared, which is we now know is 9 radians per second. So this will give us an energy of 0.089 joules. And last but not least, what is the ball's angular momentum about its center of mass? And we know that L is equal to I omega, so this is just 0.0022 kilograms meters squared times 9, which is just 0.02 about kilograms meters squared per second. That is just what the units are. That's kind of just how they work out. It's not, there's no special trick here. So this again was also a plug and chug. For the last problem, upon reviewing the last problem further, I realized that this is actually not an energy or rotational momentum problem, and I would rather focus on those. So if you would like to know the solution to this, you can come ask me personally and we can talk about it, but I'm actually not going to use this video to go over it. I would not give you a problem like this because this is more of a, like I said, more of a torque kinematics, rotational dynamics type problem. If I were to ask something, for example, that was more like, so take a break now, you can finish this problem, or we can talk about it in school, whichever, and when you're ready, come back, press play, and we'll go through the solution. Alright, I'm assuming you've actually tried the problem, so let's take a look. So this is going to be an energy problem because there's also this change in height, which means there's going to be a change in gravitational potential energy. We did a problem similar to this on a quiz that I will have given back to you by this point. But let's take a look. So I'm assuming that they're both starting from the same height. We'll call this 2, we'll call this 1, and we'll make 1 the heavier one. So let's make this a little bigger. And let's say they start from the same height. What I'm going to do is I'm going to set the 0 reference point to be 1 meter below the heaviest one. That way, when the heaviest one gets down here, it's not going to have any gravitational potential energy, and only this one is going to have gravitational potential energy. So, we can, and this is going to be our system, is going to be all the things as well as Earth, so that we can have this gravitational potential energy. So looking at the bar chart, which I will set up over here, we start off with gravitational potential energy for 1 and gravitational potential energy for 2 and nothing else. There's no work done here. Alright, they both have, well, actually that's not true. Technically, 1 should have ever so slightly more. And then when we're done, 2 is going to have some more gravitational potential energy. I'm just going to make a few changes here. There we go. 2 is going to have slightly more gravitational potential energy. All right. There we go. So 2 is going to have some slight more gravitational potential energy, as I said 3 times. So that's 1 more for that. But then also all of them are going to have kinetic. And the pulley is going to have some rotational. Okay. Notice I gave both of them the same amount of kinetic, which I guess I probably shouldn't have because 1 is going to have technically more kinetic energy than the other. So let me fix that. There we go. And we can assume that the rotational and the kinetic for the other one are the same, just for the sake of it. All right, there you have it. So our equation is going to look something like this. Ug1 plus Ug2 is going to be equal to, now Ug1 now has no gravitational because it's down at the ZRP at the end. So we've just got U, and this is all initial. I don't know why I wrote F, initial. And this is Ug2 final, KL1 final, KL2 final, and K rotational final. Plus. There we go. So plugging all this in, it's going to be a doozy. We've got M1 G H initial plus M2 G H initial. Notice these H initials are going to be the same, so we can simplify this in a little bit. And this is finally going to be M2 G H final, which is going to be twice, or it's going to be, yeah, twice H initial, because this will have gone down 1 meter, which means this will go up 1 meter, and so it's going to be twice the initial height, plus 1/2 M1 V squared plus 1/2 M2 V squared, notice these V's are the same, plus 1/2 I omega squared. So we can start plugging things in here. And remember, we're looking for the final velocity for one of these crates. In other words, we're looking for V. We will have to find omega in terms of V here again, even though I keep telling you you don't always have to do that. But we do. So let's simplify a little bit to make things easier for ourselves. We can factor out the GH initial here. So we've got M1 plus M2 GH initial is equal to M2G, and I'm going to write this in terms of H initial because it'll help us out later. H initial, and this is going to be times 2 now because, again, this is up here, plus 1/2 M1 V squared. Oh, and I'm going to factor out the 1/2 V squared here to make this calculation a little simpler. 1/2 m1 plus m2 v squared plus 1/2. Now, for our disk, we have, well, we're actually given the moment of inertia for the disk, so there's no sense in rewriting it. Although, one problem here is we don't actually know no, we do. So it's fine. Never mind. So there's no sense in rewriting this. And omega we can write as v over r disk, right? Squared. This v note is the same as these v's, this v over here. So let's start combining like terms. I'm going to combine the two terms here that have the v squared in it, and I'm also going to move this over to this side. So we've got m1 plus m2 gh initial minus 2m2 gh initial, which we can simplify further, is equal to 1/2. I can factor out this 1/2 again, and we've got m1 plus m2 plus I over r squared, right? This is now v squared over r squared times v squared. And if we continue our simplifications to make things easier for ourselves later, we see that we can factor out this gh initial again, and we've got m1 plus m2 minus 2m2 gh initial, which is actually just going to be m2 minus 2m2 is going to be minus m2. So we got m1 plus m2, minus m2 minus m2 times gh initial is equal to this mess. 1/2 m1 plus m2 plus I over r squared v squared. Simplifying this, or solving for v squared here, we've got 2 m1 minus m2 gh initial over m1 plus m2 plus I over r squared. And then v would be the square root of this lovely mess we've got here. And so after plugging everything in, you'll get some number, which I don't feel like doing right now, so I'll leave that up to you. That's that. We will talk tomorrow. Please come with any questions you still have, and that's it. Have a good night.